Okay, all right, so example 4, it says to find the missing sides. So this is just going to be a little bit more of algebra, okay? So what we're going to do is, it says this is a square, okay? So this is a right angle. So if I was going to do the Pythagorean theorem here, first of all, notice, all right, why do these two side lengths have to be the same? Remember, it's a square, all right, which means that the side lengths of a square are the same. So if I was doing this, C has to be my 2, all right, because it's my hypotenuse. And so if I'm setting up this example, I'm going to get x squared plus x squared equals 2 squared. All right, well, how many x squares do I have now? I have 2 x squares is equal to 4, all right? Solving this, I'm going to divide out the 2 first. So I'm going to get x squared is equal to 2, which means that x is equal to the square root of 2. And that's as far as you can go. That's our final answer. Okay? All right, next one. We have a right triangle. Okay, so this is our right angle. 10 is going to be our C, and then the other 2 are A's and B's. Okay? So let's go ahead and set this up. So I'm going to have x squared plus, all right, x plus 2 squared equals 10 squared. Okay. From here, I'm going to bring down my x squared, but remember, we're not allowed to take this 2 and distribute it through. All right, that is not good. You're not allowed to do that. What you actually have to do is remember what it means to square something, which means to multiply by itself, right? So we actually have to FOIL x plus 2 times x plus 2, which would give us x squared plus 2x plus 2x plus 4, all right? Which when I combine everything together, I'm going to make it pretty, and I'm going to move it up here because I'm running out of space. I'm going to get 2x squared plus 4x plus 4 equals 100 because of 10 squared, okay? All right, now remember with quadratics, okay, has to be set equal to 0, so I'm going to subtract that 100 over. So I'm going to get 2x squared plus 4x minus 96 is equal to 0. All right. And then what I'm going to do is so you could factor this, all right, but what I would notice is that all of these are divisible by 2, all right, including that 0. So I'm going to divide each of those by 2, so it makes it a little bit easier to factor, all right? So I would get x squared plus 2x minus 96 divided by 2, oopsie, minus 48 is equal to 0. Okay, so now I'm going to factor this, all right? So I need to find 2 numbers that multiply to get a negative 48, add to get a positive 2. Those 2 numbers are 8 and a negative 6. So I'm going to get x plus 8, x minus 6 equals 0. All right, setting them both equal to 0, I'm going to get x is equal to a negative 8, x equals a positive 6. All right, the negative 8 won't work because we're talking about side lengths, so my final answer is x equals 6. All right, guys, so the next idea is a Pythagorean triple. All right, and what a Pythagorean triple is it's 3 whole numbers. All right, so remember, whole numbers means no decimals or fractions, okay? So 3 whole numbers that satisfy the Pythagorean theorem, all right? So what this means is that there are common side lengths within these triangles, within right triangles, that satisfy the Pythagorean theorem, all right? But they have to be whole numbers, okay? So one of those is a 3, 4, 5 triangle, okay? And so if I would plug that into the Pythagorean theorem, all right, which of those side lengths has to be my hypotenuse? Well, it has to be the biggest, so 5 has to be my hypotenuse, okay? So if I plug those in, what I would get is 3 squared plus 4 squared equals 5 squared, all right? 3 squared is 9, plus 4 squared is 16 equals 25, and that's true, all right? So what these are common Pythagorean triples, okay? Same idea as if I took 5, 12, and 13 and plugged it into the Pythagorean theorem, it would satisfy the equation. All right, 8, 15, and 17 also, all right, would satisfy that equation. And then 7, 24, 25, okay? Now, if you look underneath each of these that I've highlighted, all right, like for example, look at this column right here, okay? 3, 4, 5 is like the base triangle, all right? But then if I have 6, 8, 10, how did I go from the 3, 4, 5 to the 6, 8, 10? Well, I just multiplied them by 2, right? So the proportional or similar sides, all right, from these base triangles are also common Pythagorean triples, all right? Meaning if I took the 6, the 8, and the 10 and plugged it in to the Pythagorean theorem, it would satisfy the equation, okay? So if you look down here, 3x, 4x, 5x, that's saying is that you can multiply that 3, 4, 5 triangle by any number and it would still be a right triangle, okay? And that's the same with this, with all 4 of them. Okay. So the next idea here, all right, is the converse of the Pythagorean theorem. So if we scroll up, all right, it says if a triangle is right, then the side lengths satisfy that equation, a squared plus b squared is equal to c squared, okay? The converse, though, is saying that, and I'm going to just kind of make these ones really quick, all right? But what the converse is saying is if 3 side lengths satisfy a squared plus b squared equals c squared, then it's a right triangle, okay? But I want to kind of write that differently. So what the converse of the Pythagorean theorem says, all right, is if I take c squared, all right, and I'm going to draw this circle in there, all right, and I plug in a squared plus b squared. So I have 3 side lengths of a triangle, okay? And I plug them in, and if each of these sides balance out, which means that they're equal to one another, all right, then that means it's a right triangle. Okay, so for example, all right, if I gave you something like, let's do 9, 12, and 15. All right, and let's say I plug those into the Pythagorean theorem where 15 has to be c, right? So if I did 15 squared, and I'm going to compare that to 9 squared plus 12 squared, right? 15 squared is 225. 9 squared is 81. 12 squared is 144. And then if I added 81 and 144, I'd get 225. So do you see how these would balance out, that they're equal to one another? We know that that triangle then would be a right triangle, okay? Now, they're not always going to be right triangles, okay? If you think about the other 2 triangles that were based off of the angles, we had acute triangles and obtuse triangles, right? So same idea, and I want you guys to start with the c squared, mostly because of the way that we connect greater than and less than in our head, all right? But what this next theorem is saying, and I'm going to condense it, all right? It says that if you take c squared and you compare that to a squared plus b squared, and we find that c squared is greater, all right, than a squared plus b squared, what that means is that we have an obtuse triangle. So the reason why I want you to start with the c squared is because, all right, this greater than, when we're talking about it in terms of the c squared first, all right, a lot of students make that connection better to it being obtuse because we think of like greater than 90 degrees, okay? Like if we would have switched that around though, and we would have had a squared plus b squared would have to be less than c squared, all right, it's the same concept of what we're doing up above. All right, the difference is that in this one we have less than, and I just think that the greater than makes a better connection to obtuse in our head, okay? All right, let's try this one. So this one is then saying if you take c squared and you compare that to a squared plus b squared, okay, and c squared is less than a squared plus b squared, then that triangle is an acute triangle. Okay, so again, I want you to start with c squared because I think that just makes better connections in our head. Okay, all right, I'm going to pause there, and then when we come down here, we're going to do these, all right, so that we can apply those 3 theorems.